Recording. Okay. So this was the question given in the last class. So I asked you to actually try to solve it. In order to solve this, you were supposed to like take help from uh the figure 6.37 as well. So I have also mentioned it because since there is now the uh, like a complex Boolean function, so basically you have uh, a compound Boolean function where we are ANDing, like it is ANDed with like two Boolean expressions or two relational operation or two relational operation results are ANDed with each other. So, like for this compound sort of Boolean expressions, we were supposed to use any of like this expressions or any of this like production rule here. So, okay. Now, just a minute. Can I hide it somewhere? What is this? Okay. Hmm, cannot see it properly. Okay, now I think it's visible. So here is the production rules, or basically the grammar for the Boolean expression which is inside the condition, and there is the normal uh, grammar for the conditions, which are basically while, if, and like if, else, and if. So now, in order to solve this, let's let's try to implement it using a grammar, like this grammar to the left. So at first, what we are supposed to do is we need to see P. So in order to see P, we have to see S. And in order to see S, we have to produce this production rule. So we're working or dealing with basically this production rule. And S produces if, then we will have parenthesized B, then parenthesized we have which one? This one. Like I didn't get your question. Could you like repeat? Oh yeah, like this is the grammar for the input string. This string, this input string we are getting, this falls under this production rule because it has a if, it has a like by a Boolean function. Like this is a let's say complex or compound Boolean function. Then we have statement one, which is inside this part. Then we have the else part, which is this one, and finally S2, which is in the else portion, like the code inside the else portion or the statement inside the else portion. Okay, yeah, okay. So now we were parsing the tree of this expression. So this is basically this if, and this is the parenthesis. Then we have this B. Now, in order to see B, we have to at first go through this Boolean expressions, isn't it? So here we can like in case it was a single Boolean expression, we would have simply done it using this manner, like whatever is written here. In case of single Boolean expression, so this production rule is basically for a single Boolean expression, like not the compound one where we are like in this case we are doing what we are doing like ANDing two operators. I mean, sorry, two operands, two Boolean operands. Now, in order to perform this operation, we need, or we will be requiring basically this Boolean expression, or this production rule, or the second production rule of the Boolean expression, where we are B equals, or B produces B1 and B2. Now, in case of AND operation, because here, if you see, we're doing what? The left hand side, we have a relational operation. So the right hand side, we have another relational operation. However, the results of them are being done what? We're doing AND here. AND operation is being performed. That's why I'm taking this AND operation, like the production rule, which is basically for the AND one, the second one. So now, okay, now, like, what is the what are the outputs of the, like in case of AND? In case of true, like both are true, we get output of one. But in case of, like, any of them is a false or a zero, we get what? The output is basically the output is basically zero or false. This is the case, isn't it? For AND, this is the truth table for AND. Now, if one of them I find that that's a true, like can I confirm that I will actually be able to get inside this statement or the if condition? No, isn't it? Rather, I have to check whether the other condition or the other Boolean expression is also giving me a result of one or not. If both are true, then only then I will be able to get inside this if condition. Else, if one of them I get a zero, like any one of them of the Boolean expression I get a zero, then I know there's no chance of me entering this S1 statement. Hence, I should go to the other portion or the else part. Okay, so if that makes sense, let's try to go through this. So okay, so now let's solve for the B's part. Now B produces, according to the second production rule, B produces what? B1 ampersand, sorry, B1 ampersand B2. Now, in order to see B completely, the cursor is to the left. I need to see B1 completely. Now, B1 represents what? See here, this whole thing represents B1, and this whole thing represents what? B2. So B1 is representing what? A relational operation, isn't it? So, yeah, like since this is representing a relational operation, we are going to implement this production rule, where it says there is a relational operation performing, where to the left we have E1, like one of the expression, and to the right we have another E1, like another E. So here this small b should be represented by E1, and this C should be represented by what? E2. So let's deal with that. So for B1, we will have E1 relational operation. In this case, relational operation is basically the less than, sorry, is the greater than, less than sign, yeah, less than sign. So E2. Now, in order to see B1 completely, like in order to move this cursor to the right part, we have to see E1 relational operation E2 completely. So still so far the cursor is very like to the very left, which means to the left of E1. Now for E1, we know the production rule of E1, like we have seen like so far in the previous lectures that E produces basically what? You can produce ID, or you can also produce like ID array, or we can also produce a like multi-dimensional array. Like this can like go on, isn't it? So in this case, we require E as ID. There is no array here given. We are requiring E to produce simply an ID, an identifier, which is in this case the first identifier is A. If I'm not wrong. Oh no, sorry, it's a B. Sorry. So the ID is basically pointing to B. So that means E dot address, like, based on the previous production rules we have seen so far in chapter in section 6.4, 6.3, 6.4, E dot address will be basically now pointing to B. So once we have received this B, we have seen E completely. E has been seen completely. Then we move to the right or shift to the right. Now relational operation is basically pointing to what? This relational operation is pointing to this less than sign. So we shift to the very right, and then we need to see E2. And E2, again, using the same production rule, which is E produces ID. This ID is pointing to what? Pointing to C. And we know this E2 will have a address attribute that will have basically C here. Okay? Like so far what I'm doing here is basically based on the production rule we have seen from section 6.4 of chapter 4. So those are like very like we have seen that multiple times. So like I'm not actually writing the production rule here. Like you know how it go, like how what the production rule actually is, and you can also like check the book, and there is the symmetric rule given. So this points to the C. If that is the case, then we will perform this relational operation where it says basically b dot code. So we are simply generating the tree address code directly. So b dot code means this will have a code attribute, and that will point to, or that will have or concat whatever is given here. So let me write it here. Now, also, we have also seen in the production rule for the e producing ID, this E1, like this E also will have a code attribute, and that code attribute will be simply empty string. Similarly, this E2 will have also a code attribute, and this will be basically empty string. Now, why is that so? Like empty string because of the production rule of section 6.4. So if you go to section 6.4, like I cannot go here, like since I have not opened the book here. So if you go to section 6.4, there is a production rule. You will take a look there. You see that when E produces ID, the semantic rules they're given is basically E dot address equals to top dot get ID dot lexeme, and E dot code is equals to empty string. That's the semantic rule for E producing ID. So if you haven't gone through those parts, then you should be like going through those previous production rules, like previous grammars and the previous lecture notes, so that you are up to date with why E producing ID should have this E dot code as empty string. So try to go through those lectures. Those are covered in the physical classes. Yes, sir. Yeah, obviously the production rules will be given. The production rules and the semantic rules will be provided to you. You will be most probably asked. I'm openly also saying you will be asked to basically write the tree address code, and you will be basically given like one of an example of the control flow. So like any of the three, rather it might be for if, or might be while, or it might be for if and if else. So based on the examples we are actually doing, like one such example will be also provide like given as the question to the next quiz which we'll be having on this Thursday. Okay, so since that was the symmetric rule for E producing ID, yes sir. Mm, like if I like the rules basically, yeah, more or less what we are constructing in terms of bottom-up parsing, it is sort of universal. For bottom-up parsing, you can think this as sort of the universal production rule until you are doing some complex sort of computation. This is basically how like intermediate representation is basically generated. So yes, you can actually take that as an like example, or basically uh, I will try to actually maybe like if there's these expressions, I'll try to give or provide the production rule as well. So if not the entire grammar, I'll try to provide as much as it is required. I'll provide that like up until that portion. So if only let's say E producing L E is needed in your like Boolean expression, then I will provide that production rule, that specific production rule, and the corresponding semantic rule. Is that fine so far? So like yes. Okay, now so B dot code now like for like if we have seen B producing E1 relational operation E2, we're directly generating the B dot code, which is the three address code, which says concat E1 dot code with E dot code, E2 dot code. So now you see, since we haven't actually performed any operation in this expression like E producing ID, we just had we just placed whatever the lexeme was from the symbol table to the e dot address. Now the e dot address is basically pointing to that location in the symbol table. The e dot code must be actually empty for this portion. We're just bringing the reference from the symbol table where has been located, and we're pointing to that e dot address. There's nothing to generate here, like no three address code to be generated here, isn't it? Like this doesn't point to like we are not generating or we are not uh, producing any temporary variable, as well as we're not performing any sort of, let's say, this sort of operation here. Nothing has been like performed here. We're just simply pointing to some location in the symbol table. Hence, we do not require actually to like generate the three address code in this case, like for E1 dot code. Hence, E1 dot code is basically empty. And why empty string? Empty string is basically because of this concatenation. In order to perform string concatenation, we require like something or some string to be present there, isn't it? String type should be present. The minimum length of some string is basically what of empty string. That's why this E1 dot code is basically presented here. Now, this E1 dot code it could be an expression. If A plus B has been given, in that case, E produces what? E plus E or E1 plus E2. Now that would have been resulted in what? That would have been resulted in some three address code. Basically, T naught equals to A plus B. That will be the three address code for this expression. If this was actually given, or this was the expression here. In that scenario, E dot code will be some code, which is basically this code, this three address code. So to generalize, like the reason or the motivation of compiler is basically what? Since we cannot go to like instruction by instruction, like we cannot generate billions of lines of codes by like hard coding things because scenarios are different for different approach, like different intermediate representation. We're how we are dealing with this scenario is basically we're generalizing things. So whatever the E1 dot code is, I don't care if it is an empty string or if it is some sort of expression. I really don't care that much. Whatever it is, simply append it, and to that append e2 dot code as well. If now that makes sense why e dot code is basically empty here. Since no operation has been performed here, it is empty. If operation was being performed, then in that case wouldn't have been actually empty. So if, for example, this is a very simple expression given here, in your question, the quiz question, like I'm also giving some hints here, like how the quiz question could be. One of the scenario could be b less than, let's say, a plus c. Now you see, this is basically e producing id, but this is what? E producing e1 plus e2. So now you will have some expression, and that expression will generate what? Three address code. Hence, your E2 dot code in that scenario will be not empty. Okay. Okay. Now E2, E1 dot code and E2 dot code is, since they're empty, I can skip them. And to the next part, I have what this portion, which is generate this three address code, which is basically saying if E1 dot address. Now, what is E1 dot address pointing to? Basically B, and it is saying relational operation, and the relational operator is what? The less than sign. If B less than E2 dot address. Now here see, relational operation will have what? An op attribute, op op or operator attribute. That op attribute will hold this relational operator itself. Okay. For example, how we have received ID dot lexim provided us with the name of the identifier. Similarly, relational operator or rel.pop will simply point us to the reference of the actual operator, the relational operator. Hence, the three address code will be if b less than e2 dot address, which is basically what? C. Then what it says? It says go to b dot true. Go to b dot true. Now, so far, I don't know what is b dot true. I have no idea of whatever is b dot true. Whatever is b dot true, I have no constant. Like still so far, I have no constant. Let's place b dot true so far here. Now, from the flowcharts, we have covered the box sort of diagram. We started, and there is this b dot code, and the outputs are what? B dot true and b dot false. B dot true is basically referring to what? Some level, isn't it? So this is, let's say, b dot true. We also have seen like, there are certain levels named as L0, L1, L2, L3. These are the levels which we will be implementing. Now we do not have any idea what this b dot true actually points to. Is it b L0, L2, L1, L2, or L3? This will be generated within this, like the parsing of the table, the parsing of the parse tree. So let's see, so like how this label is being created. So let's try to complete the parsing of the tree, and this beta2 will be solved by itself, like as we go above the layers of the parse tree. So it says if b is less than c, go to beta2, and to the next line it simply says go to b dot false. Now why is it so? Can anyone tell me why after this line there is this go to b dot false? So we have this one, which is basically saying if b is less than c, that means if this is true, then go to b dot true. Then there will be this b dot true level where we jump to. But if this is false, then we should go to some b dot false area, which is, let's say, somewhere here, b dot false. That's what it is referring to. So this is so far the three address code we have generated. for performing this much of the or parsing this much of the syntax tree. Now, since we have this b dot code here, now we can go, or we have seen this b1 so far. So we place this cursor to the very like to the right of this b1. Then again we shift this cursor for the end portion, and this the and or ampersand is a terminal itself. Now, in order to see b2 again, we have to implement or derive the production rules of B in order to get C greater than A again in that format. So B simply have E1 some relational operation with E2, and the cursor is to the left. In order to make the cursor go to the right, we have to see E1 relational operation E2 completely. The cursor is to the left, which is this E1, and E1 points to ID. We know from the E producing ID production rule. And this ID points to what? This ID points to basically C, if I'm not wrong. C, yeah. C. Hence, E dot address will be basically C, and E dot code will be empty since no operation is being performed. Relational of points to what? This less than sign again. Oh, sorry, no, this is the greater than sign. The greater than sign. So the cursor moves from here to here, then again from here to here, and finally from here to the E2. But for that, we have to see E producing ID. ID points to C. So I mean, so the ID points to, or ID dot exit points to A. Hence, E dot address will be A and E dot code will be empty string since no operation. So far, we have seen up until E2. Then B dot code will be something. B dot code will be again, this is for B2 dot code. The code will be E1 dot code concat with E2 dot code. Now E1 dot code is empty string. Here E2 dot code is empty string. So we can ignore them. What we will have is if E1 dot address, which is C, relational operation or operator, which is greater than what? Sorry? Yes, it does mean concatenation sign. Okay, so if C is greater than A, then go to again, here it says B dot true. Now, what is this B dot true? This is basically B2 dot true, isn't it? Here, this B dot true was for what? This B1, isn't it? It was for this B1. So to make things much more clear, let's write here B1 dot true. And for this portion, go to B dot true basically means what? B2 dot true. Because according to this production rule, this B is referring to, in this case, this B2. So things will be much more complex if we write only B. So let's point it out in terms of actual B2 and B1. So go to B2 dot true. And if it is false, then go to B2 dot false. Hence, this will also be B2 dot false. So we have received, that means we have received up until B2. So we have seen B1 and with B2. So that means we can now perform this production rule, which is we have seen up until this much. So once we have seen B producing B1 and B2, what do? We perform, or we have this as the B1 dot true. So this B1 will have some true attribute. So B1 will have this true attribute, and that will generate new level. So this level is, let's say, L1, the first level. since we haven't created any level yet, so this is the first one, first level. Then we have b1.false. So b1 has a false attribute, and that simply points to b.false. Now, what is this b.false? B.false is basically this head b, so it has now a false attribute. Now so far, I do not know what this b.false actually refers to, but I will like go with the flow so that things works out at the very end. So far, we have seen b1.false is basically b.false. Then we have b2.true. So b2 will have an attribute which is true, and that will simply point to b.true. So basically now b will have a true attribute as well, and b2 will have a false attribute here. That will basically point to what? b.false. So b.false already has been declared here. If nothing else is being shown. Yeah. Now we generate the b.code. Now this b has an attribute called code. So let's see what this code will refer to. Here, this was the tree address code for this b2, and this was the tree address code for what? b1. So where should I write tree address code for b, the b? So let's write it here. This is the b.code part. This will have what? This will have b1.code. So b1.code is basically referring to if, so basically this one. So let's write it. If b less than c, go to b1.true. Now remember, b1.true refers to what? See from here, b1.true refers to L1. So new level is basically L1. So we can write this as L1. Yes, b1.true basically refers to L1. Then we have, yes, sir. See here, from this production rule, when we have seen b producing b1 and b2 completely, the first semantic rule is b1.true is new level. So whenever we have a new level, we generate a level with a number. Now, what is that number? Since so far, while we were parsing, have you seen any new level being called? No, this is the first time we have called new level. That's why, like, this is the first, like, since this is the first level, we are marking it as L1. So now, in the subsequent calls of new level, whenever we will call a new level, that will actually increment from what was the previous level, which was in this case, let's say L1, and we will place the incremented value and place it here. So now, whenever we will call, let's say for this case, if this is the second new level we are calling, then that will be basically generating L2, and the reference will be placed to b.false or b.true, wherever this new level is being called. Like, does it make sense to you now? Okay. So let's return back here. This was the first portion. So b1.codes portion. Again, go to b2.false. Now b2.false points to where? See here, b2.false basically points to b.false. So we can, instead of writing b2.false, we can also write here b.false to make things simpler for us. So b.false here. Let's write b.false. This was for b1.code. After writing b1.code, we are concatenating the new label which we have created. What was the new label? Basically this one. So which is L1. So this is the L1 now. This is the L1 portion. Like for simplicity to understand, this is the level, we will place a colon here. Like for our understanding, we'll place a colon here that this is a new level, the level we created just. We appended it with this b1.code like immediately after this b1.code. And after this L1, we append this, or we're appending this b2.code. b2.code basically points to whatever is provided here. So which is if E is greater than A, go to b2.true. Again, b2.true points to what? b.true. b.true. So go to B dot true. And immediately after that, we have go to, yes, sir. Where's sir? Oh, label B1 dot true basically refers as this is the label we just placed in B1 dot true. Now in B1 dot true, what was the label we placed? This is basically L1. So that's what it is saying. So in the 3 address code, mark this as a label. This is the label. That's why I placed the colon mark here to represent that this is a label. So for example, there is this production rule, symmetric rule here. It says gen. So we're generating 3 address code. Similarly, there's another function which is label, similar to generate function, where it says mark whatever is inside this as a new label. And we mark this as what? L1 already. Hence, this label means we're placing L1 and with a colon to refer that this is the new label. So whenever we call to this label, we can jump to that instruction immediately. That's why this label function has been called. Does it make sense now? Okay, sir. So we were up until here. And for this portion, b2.false refers to what? b.false again. So for simplicity, we're actually sticking with the header, like the production heads attributes. So b.false. We're not like dealing with a bunch of b's. So we will have b1, b2, b3. Like we're trying to simplify it as as low as possible, so that we have only one b in our tree address code. So that while we are replacing these b attribute values with some original values or labels, we can do that as easily as possible. Because once we generate things like, see here, it is already sort of messy, and if anyone now suddenly tries to get enter this class, he or she will get confused, like what is happening. So far you were with going with the flow. Now you know we are so far here, and we have generated this tree address code as we approached or propagated upwards. So we have seen up until this much, and this was the b dot code generated, which is points to basically this b. Now, where did this come from? This actually come from this b. So if L parent b, we have seen b, we have this R parent. So we have also seen, let's say, this R parent. And after this R parent, what do we have? We have a S1. Now we have a S1. So what should this S1 points to? Remember, S1 or here, S points to what? S points to some other statements. So here, this S1 will point to some, let's say, we have 2 instructions. One is this, another is this one. So we will have 2s. So this will be basically pointing to, let's say, S1 1 and S1 2. Now why 1 1 and 1 2? That's basically from producing from this S1. That's why this 1 is basically placed here. And this 1 and this 2 is basically for, according to this production rule, we have the left S and the right S. So this is S1 2. We have seen so far up until this much. So the cursor is to the very left. Now S produces what? According to this production rule, S produces assign. Now, like one of you have asked me this in the physical class, and the Saturday, most probably in the Saturday's class, that why assign is there, and what does this semantic rule, or how this assign dot code is placing its value to S dot code. This assign basically refers to, as I have mentioned earlier, we have seen from from section 6.4 that S can generate, like S can produce what? S can produce some ID equals E production rule, or ID equals L production rule, that sort of thing, or L equals to E production rule, isn't it? So that's basically what I'm referring to. So that S could be actually referring to ID equals E, assignment operation. This is doing what? Some assigning operation. Hence, this is like since this is also an assigning operation, we are actually contribute or attributing this as what assign operation. So whatever three address code will be generated using the production rule from section 6.4, that code will be simply placed to this s.code. So we are like if we like go to that production rule and do it again, this will take a very long like this lecture will become maybe 3 to 4 hours of lecture. So let's not do it in that way. We know we have seen previous lectures how this assignment operation is being performed and how the three address code generates, and we know that for this operation, what will be the three address code? The three address code will be basically. Just a second, let me erase this out. The three address code will be basically what? This assign for let's say the S11, I mean this 11. For this one, let's write the equivalent three address code, which is basically T not equals to let's say B and B equals to sorry A equals to T naught. Then for the second one, we have T1 equals to T1 equals to A, not necessarily A, rather T naught plus B, and placing C equals to T1. So this is basically the three address code for the first, like for the S11. So S11, I mean, sorry, S1 basically. S11 will be the assigned code, or S11 dot code will be basically this one, which is T naught equals to B and A equals to T naught. This will be for S11 dot code, and S12 dot code will be T1 equals to T naught plus B and C equals to T1. Hence, S1 dot code will be assigned dot code simply. So that will basically point to this code portion. Since I don't have space to write here, I'll point to this as the code. So let me point it with some other color. So let's say S1 dot code basically points to this box here. Now, this was for S1 dot code. Now, after S1, we have what? After S1, we have an else. So this will again produce else. Else is a terminal itself. So we don't have to perform any operation for that. Like since we don't have any symmetric rule immediately after else. So the cursor moves from S to else to that part. And finally, we have this S2. Again, S2 is basically which portion? This is the S2's portion. S2 will have like point to what? S21. So we will have here S21 and S22. And S21 dot code will be this portion, and S2 dot code will be this portion. Hence, S2 dot code will point to the first one will be, let's say, since we have worked with T naught and T1, this will be T2 equals to A, then B equals to T2, then we have C equals to, let's say, T2 minus, sorry, T3, no, not C directly, but T3 equals to T2 minus A, and then C equals to T3. That's basically S2 dot code, isn't it? So this is the S2 dot code. Yes, sir? Yes. Pardon? Oh yeah, sorry, I for like I forgot the symmetric rule. Sorry, yeah, like you have reminded a very good thing. Pardon me. Like I have missed this symmetric rule. I was supposed to follow the symmetric rule. Symmetric rule. Wait. Then I have to go back. So we had this S1, 1, and S1, 2. Now, so for the codes portion was fine. So S1 dot code will be basically, since we have generated so far like this much, let me erase some of the portion. So I won't be requiring, I will be requiring things here. How am I supposed to deal with? Okay, let's try to make this screen a bit larger to the very right. Let's extend it. Okay, let's see. Okay, that's the case. Then let's try to place this S1 over there. So we will have, okay, now let's say, yeah, from there we will have this S1 here, and this S1 will be basically pointing to S11 and S12. Now S11 will be pointing to assign, and so for S11 dot code will be T naught equals to B, then A equals to T naught. This will be so far fine. And for S12, the code will be, since we are copying basically what? The assign dot code here, S dot code will be simply assign dot code, and assign dot code is basically this three address code. Hence S212 dot code will be also uh, T T naught, so T1 equals to T naught plus B, and C equals to T naught 1. Like this will be, like this is basically copying assign dot code to S dot code, S1 2 dot code. So this is the code for assign as well. Okay. Now the semantic rule for S1 is basically this. So S1 will have a next attribute, which will be new level. That means we will generate a new level. Now, so far, try to like go back a bit and see, have we already generated any level so far? We did, isn't it? We did L1. So now whenever we will generate a new level, that will be basically the next incremented value, which is basically 2, L2. So we now generate this L2 or level 2, and sorry, not for S1. This is for not this S1. This is for this S1, S11. So this will have a next attribute here. Because see this production rule, this says, okay. So if you see this production rule here, it says S produces S1 and S2. And this S1 dot next refers to this left child. So similarly, the left child for this S1 is basically S11. Hence the S, like the dot next or new level will be created for the left child. So S11 dot next, which is now L1. Then we have S2 dot next as S dot next. So this will have a next attribute, but this one two will have a next attribute which will be pointing to S1 dot next in this case. Finally, we have S dot code, which is basically this header. So that will point to S1 dot code. So S1 dot code will be S1. Let me write it below. So this is for S1 dot code. This one. This S dot code refers to this S1 dot code. And we will have at first this S11 dot code, which is T naught equals to B, A equals to T naught. And then we have what? Then we have new label, which is S1.next, which is basically this label we just generated. So L1, sorry, L2, not L1. I have already generated L1, so this is L2. Pardon, I'm making mistakes today. So L2, then basically after S1.code, we have the label, and finally S2.code, which is basically this one. So T1 equals to T naught plus B, and C equals to T1. Someone is trying to join, and he or she won't be able to understand because we have made like such a mess now. Okay, so we have seen so far up until this much, isn't it? So S1 has been seen completely. Now we have an else portion. So this S will have else here, and after that we will have S2. And S2 also similarly we have now two statements. Again the same rule. So S, let me try to make it a bit take more space. So S21 and S22. So S21 will point to a sign, and it will have now a code, which is basically a sign dot code will be placed here. So the code was basically B equals to A. We have used up until T1, so this will be T2 equals to B. Oh, sorry, T2 equals to A, and B equals to T2. Then we have S22. So S22 will have a code attribute, and this will point to a sign. And the three address code or equivalent three address code will be T3 equals to T2 minus A, and C equals to T3. If that's the case, then again S produces S1, S2. We will have new level, which is over here. This dot next will be new level. Now we have seen up until L2, so this will be L3. This is L3. Then we have S2 dot next as S dot next. That means the right child will have dot next as the parent, which is S2 dot next. 2 dot next. Now that means this will have a next attribute. And finally we have S2 dot code equals to like this S dot code equals to S1 dot code. So this will have a code attribute that will basically point to, let's write it here. So now this code will point to this portion. So that is S1 dot code, which is T1 equals to T naught plus B. No, not this one. Sorry. Is it? No. So basically this one. T2. T2 equals to A. T2 equals to A, and B equals to T2. Then we have label. So here we have else as the new label, and then we append S22 dot code. So S22 dot code basically points to T3 equals to T2 minus A, and C equals to T3. So we get up until this S2. Now finally, we have seen up until this much. That means this whole production rule has been seen. So next, let's see. Now what do we do? What we are going to do is now this b.true, which we have already declared here, this one, This will be a new level. So new level is basically we have seen up until L3. So this will be L4. And B dot false will be new level, which is L5. Because after L4 comes L5. Then we have S1 dot next as S2 dot next as S dot next. So basically, this S1 dot next will be this S dot next. This will point to equals to S dot next. Similarly, see here, it says, where did it go? S2 dot next also points to S1 S dot next. So basically, left child and the right child both will have now point to S dot next. Since S dot next have been found so far, what are we left with is S dot code. So now this S will have the another attribute which is dot code. That will represent at first B dot code. So that was B dot code. So B dot code means which B dot code? This B dot code. This B dot code. This B dot code refers to which one? This portion. So this is the B dot code. So let's try to do it below here. So B dot code will be, or better write it above. So we will have here S dot code pointing to B dot code, which is basically if B is less than C, go to, it says L1, else go to B dot false. Now let's see if B dot false has been declared so far. Yes, we have for now found L5 B dot false. So L5 here. Then we have L1 placed here. Again, now execute this. If C less greater than A, then go to, where do we go? B dot true, which is L4. See, this is L4. So L4 here, or go to B dot false, which is basically L5. That was the code for B dot code. Then we have level B dot true. Now, B dot true is L4. So we will place new level here, L4. Then we have S1 dot code. S1 dot code is basically this one. S1 dot code is this one. This one is S1 dot code. So let's try to write it here. Now, how am I supposed to write it here? I have to increase it more. Okay, let's see. Okay. So S1 dot code is referring to T naught B, T naught equals to B. So T naught equals to B. Then we have A equals to T naught. Then we have L2. L2 as T1 equals to T naught plus B, and C equals to T1, if I'm not wrong, yes. Then we append with that what? That was basically S1 dot code. Then with that, we append go to S dot next. So here we will write go to S dot next. Now, what is S dot next again? S dot next. We haven't yet write any S dot next yet. So let's keep on adding. So S dot next. So here, because we have still one more production rule to go. So go to S dot next, and after that we have label b dot false. B dot false is basically L5. So L5 here now, that's level 5. And level 5 will, after level 5, we will have what? S2 dot code. So S2 dot code points to this tree address code. So let's copy it. Let's copy this portion to see. No. So this is for up until L5. So this is after L5. So I'm writing it a bit to the right so that I have much space here. L5. So this is after L5. This comes after L5. And do I have anything else? I mean, like this, that's basically S2 dot code. And so we have seen so far S. So that means once we have seen this much, we have seen S. So we have seen S. Now, once we have seen S, that means we have seen P produces S. Now, when we have seen P produces S, what do we have? We have S dot next as new level. Now, new level means what? This is basically L6, the newest level we can have. And finally, we have S dot code appended with the new level here. Now, S dot code is basically what? This was basically S dot code. This whole entire thing was S dot code. And this S dot next will be replaced with which one? This S dot next, which is referring to our beloved L5. So let's replace this S dot next with L5. So L5. And finally, sorry, not L5, L6. Sorry. Pardon. Again, I'm making mistakes. So this will be L6. And finally, we will have L6 after this. So L6. Let's write L6 here. So this is L6, which is at the very end. Now let's see if things work or have things worked so far accordingly. So it says if B is less than C, like if it is true, then we have to check if this is true or not. Because only one true won't give us the correct answer because this is an AND operation. So also if this is true, then we will go to S1. If any one of them is false, if this is the first one is false, we do not need to check the second one. We move to the next line. So let's see if it is correct or not. It says wait a minute, yeah. It says if B is less than C, then go to L1. So we go to L1 because only one true won't make any difference. But if it says, wait a minute, I have made some mistake most probably. This is s.code, and that is level b.code along with level 2. b.true is L4. Then we have inside L2 and have b dot false, and after b dot false we have s2 dot code. Okay, s2 dot code is here, and after s2 dot code we have L6. Oh yeah, it's fine. Yeah, like it's correct. So let's see. So if the first one is true, then directly we cannot say that we have entered the region. Rather, then go to L1. So L1 is the second portion here. This one is basically L1, referring to L1. So if this is true, then go to L1 and check if C is greater than A. If that's also true, then only go to the S1. This is S1's portion. So it says C. It says T naught equals to B and equals to T naught. So basically the first operation. Then we have L2, level 2 here. So level 2 is basically T1 equals to T naught plus B and C equals to T1. So this operation. once we are done with this portion, we do not need to go to this portion, this region, isn't it? We need to just simply end this if condition. That's basically saying go to L6. So here is L6. We do not need to perform L5. But however, if this is false, we do not need to check this portion, which is the next part of the Boolean expression, the right part of the AND operation. We simply go to L5. We know this is a false. We do not need to go to S1. Rather go to L5, which is S2. So now L5 is basically pointing to S2. Perform this operation, which is T2 equals to A and B equals to T2. This is first operation. Then we have second operation as the level 3, which is T3 equals to T2 minus T2 minus A and C equals to T3. And finally, we have L6 below. So this is basically the three-address code for using these two production rules. However, see one thing, we have some redundant go-tos here. Now, like, isn't it? Like, we have redundant go-tos and redundant labels. Like, we could have reduced things completely. See here, for example, let me wait a minute. Mhm. Okay. For example, for let's say, in case of, like, let's do it some like one of the example of the book, because working with this will take too long. This was the example of the previous class. That's why like I did it, how we should perform this. But let's do an example of the book, which is, let's say, wait. Okay. So, for example, if we had this expression, which is if, let's say, x less than 100 or x greater than 200, ampersand, x not equals to y, then do this operation. This is only one if condition. Okay. The equivalent three-address code using the, this two production rules, these two grammars for S and B, or the S, the same statements and Boolean expression, the three-address code will be basically this. So I'm directly quoting from the book. So if X is less than 100, go to L2, else go to L3. This is L3. Then we have if X greater than 200, go to L4, else go to L1. This is L4. Then again, if X is not equals to Y, then go to L2, else go to L1. Finally, this is L2 where we perform this Fx equals to 0 operation. And finally, the outside of the code. So this is the equivalent three-address code of the above expression. Now, see here, we have many go-tos. Now, these, like, some of them are redundant. Why redundant? See here, immediately after this go-to, we have L3. So why point to some L3 which is below me, isn't it? This is the redundancy. If it's not true, then simply we will move to the next level, like next line. Similarly, see here that, for example, if x is greater than 200, then go to L4. Now, instead of like saying here, go to here, like saying go to L4 and saying go to L1, rather we could have simply said if x is less than 200, go to L1. Otherwise, simply run whatever is below me, isn't it? So we have reduced go to by so far with like reduced by twice, like reduce two of the go to instruction. Similarly, this is also another case. And there is this instruction as well. Like if, let's say, if x is greater than 100, then only go to, sorry, we do not need to change that one. We need to change this last one. Exactly. We will require an optimization of this free address code. Now, how do we optimize this free address code? We really require this to be optimized because we have many redundant gotos. Now, how to replace these gotos here? First thing is to introduce a concept, which is if this is, let's say, false, sorry, like this, yeah, if this is false, if this statement is false, or better, let's write it in this manner. Actual expression was basically x greater than 200. Go to somewhere. Now, I do not want to perform this like in this manner, which is basically I do not want to go to some level which is just below me. I do not want to have two go-tos one after another. One is, let's say, over here, another at the very bottom instruction, like at the very next instruction. So what can we do? Now, changing this operation in this manner will hamper the actual operator. We will be modifying the source code. Why? Because source code didn't have this less than sign. Source code had what? The greater than sign. So what we could do is basically, instead of having only if, we will like introduce this if false. This if false statement simply says if x greater than 200 is false, that means if actually x is less than 200, then go to L1, which is outside of the box or outside the region. But if it is true, then run whatever is to the what is to the very next instruction. So let's say L4 was in the very next instruction and it goes on. Okay, so this is one of the like one of the keywords we will be introducing. And the next thing is this falsing. So basically, when we'll be assigning, let's say b dot true, instead of b dot true assigning to a new level, when we will be saying b dot true is equals to false, that will simply refer to that whatever is here, if this is not true, then go to this next instruction. Do not generate any labels here. Do not jump to any labels here. Rather go to that next instruction, whatever it is after me. So if this is line number 31, go to line number 32 immediately. That is what this fall instruction is saying, that fall to the next instruction. Okay, so that's basically the concept we will be introducing, this fall instruction. Now, if we consider or if we make changes to the actual grammar, what will be the equivalent production rule or equivalent grammar here, using the semantic rules? So basically, this will be the semantic rule. Let me copy it. Wait a minute. Okay, so here, where is my cursor? Here. So this is the newly given semantic rule. Now, where to place this semantic rule? Now, the first portion of the semantic rule will be placed immediately after the relational operation. So let me make some room here. Control X, Control V. Let me go here somewhere. But this needs to come here at first. There's a semantic rule we will be having here. So, yes, sir. The fall is basically going to the next line. So if we have, let's say something, this statement, sorry, wait a minute. Yeah, something, let's say this statement is here. If this condition is not true, immediately go to the next line or next instruction. So we have multiple instructions here. So fall simply like the, let's say in terms of football, what do you say? Like when we the attackers and the defenders also have gone to like the D box of the other group or the other goalpost. When you have, let's say, made a goal, or the opponent has received, or opponent has snatched the ball from you all, what do you say? Fall back. Fall back to where? Fall back to your distinguished defensive position. So fall back to the immediate line or the immediate next instruction. That's what like fall back or fall means. Okay? Like, does it make sense? Okay. So so that was for that portion, and we will be introducing this line for the OR operator or the OR operation. This is for the OR. Let's where do I find this OR? Okay, let's see. V V1 to 2. Okay, so this will be the no, where do I place this? Wait a minute. Hmm. Yeah, that will be enough. So let's go above. Okay, and this will simply go below. Okay, so now see, this will be the modified semantic rules for OR and the relational operation. So how things work now, let's see. So in the case of v1.true, in the case of v1.true, while we are generating the first tree, let's see. So let's say, let's erase this portion because we won't be requiring this anymore. So this part, yes, sir. Just a second. Just a second, sir. Yes, where? Yeah, basically. Yes. No, not necessarily, because B generates E1 relational operation E2. However, only the thing will change in that case if E1 or E was basically an equation or any expression. For example, let's say E producing, let's say A plus B plus C. In that case, only the code part, this code part will change. At the same time, E will no longer pointing to this B. Why? Because E will be pointing to now E1 plus E2, and that E2 will point to another E1 plus E2. Why? Because there are two additional operations. So that will actually propagate to this E dot code, and that this E dot code will no longer be empty. Rather, why? Because it will be appending these three E's together and having this E dot code. However, this b dot code and b dot true and b dot false will be intact. Only the thing will change is b dot code. Why? Because b dot code is simply appending what? E dot code as well. Since E dot code is now different, B dot code's only that portion, the three address code will be different. Other than that, nothing will be changing. Okay? Okay. Okay. If we have no longer a question regarding this portion, let me erase this part because I will be requiring an immense amount of storage. Let me space. Where did it go? Okay, so the production rule, I mean, so not the production rule, the question is now, the question was basically, wait. The question was if, yeah, so if if x is less than 100 or x is greater than 200 and x is not equals to y, then x equals to 0. Perform this operation. Okay, so in that case, we have seen the three address code was basically this one, but now we have changed it a bit. So how things are going to react. So P produces S produces if, then L parent, B, R parent, and S1. However, this B is basically now a combination of three Boolean expressions. So B, B1 or B2. However, this B2 is now also having B2 1 ampersand or and with it and B2 2. Okay, if that makes sense, then let's come up for the B1's part. So B1 or the OR part is basically saying we have what? There's some relational operation. So this B will be basically E1 relational operation E2 and relational operation is saying this part, which is this one, test equals to them. So test will be a new temporary variable. So let's see. We have some test variable here, and E1 dot address basically points to whatever we have here, which is, let's say, X. So X less than relational operation E2 dot address. Now E2 dot address points to 100, so we will write 100 here because either ID or number dot lexing will be provided here. If that's basically test, then we have S here. Now what is this S? S simply says that if B dot true is not equals to false and B dot false is not equals to false, then generate if test go to B dot true and generate concat with generate go to B dot false. Now how it works, let's see. So if relational operation, yeah, now if x is less than 100, in case this is true, then we say if x less than 100, why? Because see here, it says if, sorry, if test, then go to b dot true. What does test represent? Test represents the Boolean result of this x less than 100. So if x less than 100, go to b dot true. B dot true simply means b1 dot true. Here actually it refers to b1 dot true. And immediately after that it says go to b1 dot false. Okay, so here it says that if b dot true is not equals to false. So how am I supposed to know if it is false or not? How am I supposed to know if it is a false or not? What is the above production rule? It says, where did it go? Yes, sir. Just here you could you can leave it's not mandatory. The attendances are not mandatory. जी okay. Alaikum salam. Okay. Why my PC is freezing? Just a second. Oh my God, my PC is freezing. Oh, just a second. My PC suddenly froze. Hmm. Why at this moment are you freezing? We are not actually like left with very much. This is the last portion, like reducing the redundant go-tos. So if we get rid of this, then that will be, I think, good enough approach. Just a second, let me see if I can do something with this. New one, don't save, and okay, let's see. Okay, let's see what will be. Yeah. Okay, so yeah, fine. So yeah, what I was saying. Um, okay, let's get back to that again. So the example was if x is less than 100 or x greater than 200, ampersand x is not equals to y, then do this operation which is x equals to 0. Now, the equivalent tree address code was, let me write that as well. The equivalent tree address code was basically if x less than 100, go to L2, else go to L3. We have L3. If x greater than 200, go to L4. First, go to L1. This is L4. If x not equals to y, then go to L2, let's go to L1, and we have L2, x equals to 0, and finally L1. Okay, now over here, if we see for this portion, okay, for this portion where we do not, just a second, we do not have, or we can get rid of this L3, like this L3 portion. Now, how do we know if we could get rid of this L3 portion or not? That's basically using this relational operation being provided here, the rule for the relational operation here. So if I go a bit down, so see here, this relational operation should say if b dot true is not equals to false and b dot false is also not equals to false. Now, what does that mean? That simply means that in this scenario, this could generate a b dot true and a b dot false based on the block diagram we had previously. So let's say this is the b dot codes part. This entirety is the b dot codes part. So this can have a b dot true and a b dot false. So if the result which we are getting doesn't show or doesn't have, let's say, any like any such really like any sort of uh any level which is immediately after them. So let's say L3 was in this case here. So this L3 was not exactly below here. So rather this L3 was somewhere like at the very end or at the like very far away. If that's the case, then only we can actually use this instruction. So over here, since this 3 address code, we had this L3 over here. So let's say this L3 was basically over here. But in case, let's say this was saying that we wanted to perform this L3, which L3 was existing outside this portion of box, which is, let's say, somewhere here. Somewhere here. Now, if this L3 is at the very bottom, then what can we say? We can say that if this is true, even if we go to the next line, we could not find L3 because L3 does not exist at the very next instruction. Similarly, b dot false, the result of this b dot false also does not lie at the very next instruction. If both of them are not happening, that means if both the false are not happening or both the false won't give us the L3 at the very next possible instruction, only then write these two instructions, which is if x is less than 100, go to L2, and if this is not the case or if this is false, then go to L3 because L3 lies somewhere outside the range, like outside my, like, or away from my next line. However, like that's what it is being said here. If you notice or if you focus, consider this portion. Again, my PC is freezing. What is happening with my PC today? Oh my God. I think I won't be able to continue this class today. Like so, okay. Let me pack things up because my PC is freezing. Okay, let me go through like to iterate through the concept again. So the basic thing is here. Let me take a screenshot of this and place it here. So if you notice here, yeah. So if you notice here, it says that if b dot true is not false, that means immediately after this statement, in case it is true, if immediately after this line we cannot find the next instruction. That means L3 was not here. Let's consider. And similarly, b dot false also, the instruction for b dot false, the label is also not in the next possible instruction or the next possible line. In that case only, generate this instruction, which is if x is less than 100, go to L2 or go to L3. Then it is valid. However, if only b dot true is not on the next line, rather b dot false is on the next line. That means b dot false is on the next line, which is this case. B dot false is on the next line. In that scenario, don't write this code. Only write if x is less than 100, go to L2, see if test, then go to b dot true, which is basically this one. So other than that, don't write go to L3 because the next possible instruction is actually L3. You do not need to write that L3. Similarly, if b dot false is false, that means b dot false actually does not exist on the next line. In that case, write it in the reverse manner. For example, if let's say x is less than 100 is not true, rather x is greater than 100, then what should we do? If x is greater than 100 was the condition, let's say over here, if this was false, alarmingly false, wait, if this was false, then we would only check if this is false or not. So how do we check if it is false or not? Simply write if false. That means if x less than 100, this is not true, this is false, then go to L3. If this is false, then go to, sorry, not L3, because L3 is immediately after that. Go to L2 if this is false. And let me write it in this way. This is L2, this is L3. Now it's much more cleaner. Now this will make sense. Okay. If this is false, then go to L3, which is away. And if this is true, then go to the L2, which is on the next line. Why? Because it says what? B dot false is on the not the next line. So this next line is basically true. B dot true is pointing to this L2. However, B dot false is somewhere very far away. Hence, it is not false. That's why we can jump to L3 since it is not false. But we should not jump to L2 since it is false. B dot true is false. So now you will realize, or you should be able to understand, true equals to false means I have this instruction if something something. The very next instruction is what I'm pointing to. So if this is 31 number line, the jump points to 32 number line. So this is the fall. And in cases of fall, I should not place any go to instruction. That's what this is referring to. Like this production rule or the symmetric rule, that's what it is referring to. And how do we implement in terms of OR loop? The OR loop basically refers to the previous OR loop was whenever we have b1.true, we introduce simply a new line, a new label. Whenever we have b1.true, we have a new label. However, this one says if b.true is not false, that means if b.true is not false, rather far. So if true is not false, that means not on the next line, rather far. So we can also identify if something is not false, then it is far. However, if something is not far, then it is false. So it is sort of anonymous thing, yeah. So it is antonym of another one. So antonymous. So basically, if something is false, that is basically next line, and if it is far, it is something far away. You need a branch or you need a jump statement. Hence, it is saying if true is not false, that means true is somewhere far away, then generate this new line, it is valid. However, if true is immediately after, then don't place a new line, new level. And in case b1.true is not false, b1.false is false. That means b1.false immediately after this line. So that in that case, it will be something like, let's say, if x less than 100, go to L2. That means true. If true, then go to L2. But if false, then simply fall to the next line. That's what the next instruction is saying, that d1.false equals to fall. Okay, if that makes sense, then I urge you to try to modify this instruction which we did, which was basically which one? Which is basically the ampersand one or the and one, which I have given you as a homework, and this book's example. Try to do it by yourself. Try to see if using this production rule you can eliminate the go to or reduce the go to or not. So most probably, if you are able to, like, this will be very easy. So this will be one of the topic of your quiz. So try to reduce this go to based on this production or the semantic rule. And I think that's all for today. We are so far done with the intermediate representation of like normal instructions, normal source code. On our next class, that means on Thursday, we will be working with the the classes. So object-oriented programming, the tree address code or equivalent representation of tree address code of object-oriented programming. We will try to see that in the theoretical concept. And let me know if you face any difficulty. Try to do it by yourself. If you face any difficulty, I will try to provide some solution resources. Okay, like I won't be able to solve it because my PC is hanging. So I think that's all for today. Any questions so far? I think like this last portion might be a bit confusing to you, but try to do it yourself using the modified semantic rules. These two, only two of the modified semantic rules, and try to implement it by yourself. Try to do it once by yourself. Inshallah, it will be like you will get the gist out of it. So I think that's all for today. Anyone have any question? Salman, Rakib, anyone? Okay, then I think that's all for today. We can end the class here. Assalamu alaikum.